I'm Kapil, MEB18050, and I'm going to explain the assignment questions. So, question number 1 goes like: a hydraulic turbine is designed to produce 26.845 megawatt at 95 rpm under 15.24 feet of head. Laboratory facilities are available to provide 4.572 feet of head and to absorb 37.285 kilowatt from the model turbine. Determine the appropriate model test speed and scale ratio and volume flow rate, assuming a model efficiency of 86%. So here I made two columns separating the parameters for actual turbine and for the model turbine. So in left side we have the parameters for the actual turbine. The the, out, the output power is 26.845 megawatt. Net head is 15.24 feet and rotational speed is 95 rpm. And for the model turbine, the parameters are power output 37.285 kilowatt, net head is 4.572 feet, and we need to find the rotational speed. Then the efficiency of the model is 0.86, and we have to find the volume flow rate. So um, we know that the specific speed of two turbines in of two turbines of the same homologous series are same. So the specific speed for the actual turbine must be equal to the specific speed for the model. So NST for the model is equal to NST for the actual turbine. Now the expression for NST is n root p divided by h to the power 5 by 4. So n root p divided by h to the power 5 by 4 for the model is equal to n root p by h to the power 5 by 4 for the actual turbine. So in this expression, except for the rotational speed for the model turbine, we know all the parameters. So substitute the values in this expression. We get the rotational speed of the model turbine as 566 rotational 566 rpm. Now now we have to determine the scale ratio, that is diameter of the actual of the model by diameter of the actual turbine. Now from relations of similarity in fluid machines, we know that h divided by n square d square for the model must be equal to h divided by n square d square for the actual turbine. So here substitute the values for head and rotational speeds. We get the scale ratio is 0.09. That is the diameter of the actual that is the diameter of the rotor of the actual turbine is 10 times the diameter of the rotor of the model turbine. So now the third part, we need to find the volume flow rate Q. Now we know that the expression for the efficiency is power output divided by rho Q GH. So from this expression, volume flow rate can be calculated as P divided by rho eta GH. So from this expression, after substitute the values, we get volume flow rate as 3.2 meter cube per second. 3.2 meter cube per second. Now now we move to the next question, that is question number 3. The reaction which goes like this: the reaction turbines at Nigeria Falls are of the Francis type. The impeller outside diameter is 4.5 meter. Each turbine produces 54 megawatt at 107 rpm with 93.8% efficiency under 65 meter of net head. Calculate the specific speed of these units. Evaluate the volume flow rate to each turbine. Estimate the penstock size if it is 400 meter long and the net head is 83% of the gross head. Assume suitable data if necessary. So first of all, the information given to us is the type of turbine is Francis turbine. The diameter is 4.5 meter. The power output is 54 megawatt. The rotational speed is 107 rpm. Then efficiency is 93.8 and net height is 65 meter. So now our first task is to find the specific speed, dimensional specific speed, which is given by n root p by h to the power 5 by 4. So substitute the values for rotational speed, power and head. We get the specific speed 4260.3. Now we find the volume flow rate. Since eta equal to power output by rho q g h net, so q equal to p by rho eta g h net. Substitute the values, we got the volume flow rate as 90.38 meter cube per second. Then we need to find the diameter of the penstock. The information regarding the penstock are: length of the penstock is 400 meter, net head is 83% of the gross head. So here the penstock is the channel from which the fluid flow from the reservoir to the turbine, from the reservoir to the turbine. So we need to find the diameter of the penstock. Now it is given that the net head is 83% of the gross head. So from this relation we can calculate the gross head, as the net head is given to us. So gross head is 78.31 meter. Now as we also know that net head is gross head, a gross head is the summation of net head and head loss due to friction. So from this relation, h net equal to h gross minus hf, we can calculate the head loss due to friction, which is comes out 13.313 meter. Now from Darcy's Weisbach equation, we know that hf is equal to f into L by d into v square by 2g, where f is Darcy's friction factor, then L is the length of the penstock, d is the diameter of the penstock, and v is the velocity of the fluid flow. Now we replace the term v by q divided by a. Since q is equal to a into v, so from this, and a is the cross-sectional area of the penstock, which is pi d square by 4, where d is the diameter of the penstock. So v equal to 4q by pi d square. So we replace the term v by this term 4q by pi d square. Now after some rearrangements, modification, we got the final expression for the diameter of the penstock, which is 8f divided by pi square g into q square L by hf to the power 1 by 5. So here in this expression we know all the equations. Q, length of the penstock is given, head loss we calculated here, then the volume flow rate we calculate that previously here, which is 90.38 meter cube per second. So in this equation, except for the Darcy's friction factor, we know all the terms. So we need to find the Darcy's friction factor. Since nothing is mentioned about the Darcy's friction factor, we need to assume. So we know that friction factor depends on the Reynolds number. F is equal to 64 by Re. Now what will be the Reynolds number will depends on the type of flow. So here I assume that the flow is partly laminar and partly turbulent. So I take the average of the two Reynolds number 2300 and 2900, which is 2600. So it is a completely assumptional, since nothing is mentioned about the type of a material and what will be the friction factor. So here I assume this. So Darcy's friction factor comes out to be 0.0246. Now substitute this value on that expression of the diameter of the penstock, we get that diameter of the penstock is approximately 3.465 a meter. It may vary with the value of Darcy's friction factor. So the last question number 4 is: a propeller turbine has been designed to develop 22,000 kilowatt under a head of 20 meter wheels turning 150 revolutions per minute. The relevant is hydraulic efficiency 95%, overall efficiency 88%, outer diameter 4.5 meter, and diameter of the hub 2 meter. Determine the runner vane angles at the hub and at the outer periphery. Assume that the turbine discharges without whirl at the exit. So here the information given to us is net head is 20 meter, then hydraulic efficiency is 95 meter, then overall efficiency is 88%, then outer diameter is 4.5 meter, hub diameter is 2 meter, and power output is 22,000 kilowatt, and the rotational speed is 150 rpm. So first we find the blades angle at the outer periphery. So the fluid enters at the inlet of the blade at the outer periphery. We draw the inlet and outlet triangles for that fluid at the outer periphery. So here we can see that the outlet inlet and outlet triangles. So the subscript O, I give it for outer periphery, and the subscript H is for hub. So in this picture I draw the inlet and outlet velocity triangles for the blade at the outer periphery. So in the inlet triangle, u naught is the blade linear velocity, then v1 naught is the fluid absolute velocity at the location, then r1 naught is the relative velocity of the fluid at that location, then vw1 is the tangential component of the absolute velocity, and vf1 is the axial component of that velocity. So and in the outlet triangle, u naught is the blade linear velocity. Since the inlet and outlet is at the same radial distance, the blade linear velocity will be same at that location, so u naught will not change. So here then v2 is the absolute velocity of fluid at that location at the outlet, then vr2 naught is the relative velocity. Then now here v2, which is the absolute velocity, is it has no tangential component. It has no tangential component, and this is from the design of axial flow turbine. We know that v2 is equal to vf1 equal to vf2 equal to va, where va is the axial velocity. So it is from the design point of view. Okay, so now overall efficiency is given by power output divided by rho q g h net. So from this expression we can calculate the volume flow rate. Now the volume flow rate is equal to P divided by rho overall efficiency into G into H net. So substitute the values, we got the volume flow rate as 127.421 meter cube per second. Now since the volume flow rate is equal to area of cross section through which the fluid passes the rotor into the axial velocity, so from here the axial velocity can be calculated as 4q divided by pi d naught square minus dh square. So axial velocity comes out 9.984 meter per second. So we get the v2 equal to vf1 equal to vf2 equal to va equal to 9.984 meter per second. Now we calculate the blade linear velocity u naught equal to d naught by 2, 150 into 2 pi divided by 60. So substitute the values. Blade linear velocity is 35.343 meter per second. Now we know that hydraulic efficiency is given by power developed by the runner divided by power available. Now power developed, now since power available is equal to power developed divided by overall efficiency, we substitute the value of power available in the formula of hydraulic efficiency. Now since the power developed by the runner is given by the Euler's turbo machine equation, rho q vw1 naught u naught, so substitute the after little rearrangement we got that overall efficiency is equal to rho q vw1 naught u naught into eta naught divided by power developed. So from this equation we can calculate the tangential component of the absolute velocity at inlet, which comes out to 5.274 meter per second. So now we get complete information about the velocities triangles to calculate the Vane's angle. So at the inlet velocity triangle we see that the Vane angle is beta 1 naught, which can be calculated as the tan beta 1 naught is equal to perpendicular by base. Here the perpendicular is vf1 and the base is u naught minus vw1. So here tan beta 1 naught equal to vf1 naught divided by u naught minus vw1 naught, which is equal to 9.984 divided by 35.343 minus 5.274. So from here we got beta 1 naught equal to 18.37 degree. Similarly, tan beta 2 naught equal to vf2 by u naught equal to 9.984 divided by 35.343, and from here we calculate beta 2 naught as 15.77 degree. Now our second part is to find the blades angle at the hub. So the procedure will remain same as we previously done for the outer periphery. So here also I draw the inlet and outlet velocity triangles at the hub location. So since axial velocity will remain same, so v f1h equal to vf2h equal to v2h equal to va, which we calculated earlier, and equal to 9.984 meter per second. So now here then we calculate the blade linear velocity at the hub, which is equal to dh by 2, 150 into 2 pi divided by 60, and uh comes out 15.71 meter per second. So now hydraulic efficiency equal to rho q vw1h uh divided by p by eta naught. This part remains the procedure in this part remains same with earlier. So from here we calculate the tangential component of the absolute velocity at inlet and comes out 11.86 meter per second. 11.86 meter per second. Now blades angle at the hub are tan beta 1 equal to v f1h by uh minus vw1h. Substitute the values. Beta 1h comes out 68.913 degree And similarly beta 10 beta 2h equal to vf2h by uh, and beta 2h equal to 32.44 degree. Thank you, sir.